All right, this is AP Calculus BC. We're talking about parametric functions today. This is the worksheet solutions. All right, so we have to sketch this thing by hand, 4 sine of t, 5 cosine of t. So whenever I'm plugging in values for t, I need to be thinking of that is the angle. And then this is going to be the ratio over here. But the angle is 0. Is a good starting point, or 1. 1 actually wouldn't be very good. Let's try 0. So if I do 0, what I'm really doing here for the x is 4 sine of t. So I'm really saying this is 4 times sine of 0. And sine of 0 is 0. So this is 4 times 0 is 0. And for y is 5 cosine of t. So this is going to be 5 cosine of 0. And cosine of 0 is 1. So 5 times 1 is 5. And I'm not going to show all my work like that. This is going to be a little bit tedious. So let me choose another good value. Like we did before, let's try pi. If I try, let me write it underneath the 0. If I try pi, sine of pi, that's going straightly up. There's pi on our unit circle. If I, let me explain this a little bit better. So if I have a unit circle over here, pi is right here. Here's pi. No, that's not pi. Alright, so let's try plugging in pi next. So where is pi? And I can draw my pi slightly neater. Pi is on the unit circle, so if I draw my unit circle and maybe make it a little bit neater. So here's my unit circle. Pi lives right here. This is pi over 2. Here's 3 pi over 2, and this one is either 2 pi or 0, whatever you want to call it. I like using 0. So pi is over to the left. So if I say 4 times sine of pi, sine is the y coordinate. I always want to think of sine as y and cosine as the x coordinate, which is kind of flip-flop, right? You'd think those are backwards, but that's what it is. So the y coordinate of pi, that's going to be 0 again. And this is going to be 5 times cosine of pi. So the x-coordinate of this angle here, pi, is going to be -1 because I'm -1 to the left, so this is going to be -5. And I guess I should be graphing it. 0, 5, that first point, 0, 5 is right there. 0, -5, 0, -5 is right there. What's another coordinate we could try? Let's try pi over 2. Pi over 2, that's going straight up, so the x-coordinate is 0. Am I doing this right? The x-coordinate is 0, and this is talking about the x-coordinate. Yeah, I'm doing this right. So cosine is going to be 0 now. Sine of pi over 2 is going to be 1, and then 1 times 4 is 4. So let's graph 4, 0. 4, 0 is right there. And then, of course, if I try 3 pi over 2, that's going to give us -4, because now sine of 3 pi over 2, that's -1, and then -1 times 4. This is also going to be 0, so -4, 0. We have these points right here. And you should probably be able to see, oh, that's basically like a circle, but it's stretched in these weird dimensions. You can verify this so it's not doing something weird. I mean, sometimes we can have like weird things happening where it's spiraling around. This is indeed just a, is it an ellipse or is it an oval? I don't know. I don't know the technical term for this. I'm going to call it an ellipse because I think that's still correct. And let me try to sketch this to the best of my ability. So it's going to come, let me use a different color here. It's going to come out from this point up to that point. Let me try coming up a little bit at an angle, and then down to this point. Then it's going to come out like that, and down here like that. All right, so there's our ovally ellipse shape. You can also verify that by plugging in a harder value, like, I don't know, let's try pi over 3. Pi over 3 lives right here. That's pi over 3. So if I do the x-coordinate of pi over 3, that's 1/2. X-coordinate is cosine. So 5 times a half is 2.5. So 2.5. And the x-coordinate would be, sorry, yeah, so the x coordinate is using sine. I keep getting those backwards. And then sine is the y coordinate. The y coordinate of pi over 3 is the square root of 3 over 2. So this is going to be the square root of 3 over 2. And that, well, square root of 3, we should know that's about 1.7. And then 1.7 divided by 2 is about 0.85. So that's a rough approximation. I guess I can show my work a little bit better here. Showing my work, this should be the 0.5 times 5, and that's how I got 2.5. So let's go to the x-coordinate 0.85, and then 0.85, and then I have to multiply that by 4. Silly. All right. So if I multiply this by 4, let's come all the way back here. I have to multiply this by 4. Because of this 4 right here, and that's going to cross cancel out to a 2. I can do that in a slightly different color. That's 2. So 2 times 1.7 is about 3.4. And this number right here, again, came from 1/2 times 5, which is 2.5. All right. So let's go to the coordinates 3.4, 2.5. So 3.4, 2.5, 3.4, 2.5. So it's right there. And that is interesting because that doesn't look like it's a 60-degree angle. You'd think it would be up here. And is there something that we're doing wrong then? No, I think that's right. And I can even check that on the calculator too, like using Desmos. I know that this is a very long example to do number 1, but I really want to be sure that I'm doing my work. How would you check your work? If I go to Desmos calculator, let's go ahead and hide you for a sec. If I do in parentheses 4, it's going to be sine of t, comma 5 cosine of t, and I want to graph that for t values between 0 and 2 pi. 0 and 2 pi. Let me zoom out on my graph a little bit. All right, so we have the angle, or the picture here correct. So if I come back and see, yep, that looks good. And how do I find the exact point when I'm using t of pi over 3? So I could say the same line here, and I can say t is, just change this to a, and I'll do a slider for a. A is pi over 3. And that is the exact point that we found over here. And then I can even make this into a slider. So let's make this into a slider, and let's change this from 0 to 2 pi in step every pi divided by 12. Sure. And then you can see that this starts off here at 0. Okay, so that's the difference. Usually you start at 0 here, and then it comes all the way around the circle. All right, kind of cool. I feel guilty because I should be doing these as quick as possible since it is AP. It's all about time, but I want to really get that depth from number 1. Number 2, I need to make my table. So my table is going to have t values, x values, which is equal to 1 minus t, and my y values, which is the square root of t. So let's, I don't know, 0 is a really good starting point. Let's make my table here too. Keep it roughly organized. And there as well. So x is 1 minus 0. 1 minus 0 is 1. And then this is the square root of 0. And there we go, 1 comma 0. So 1 comma 0 is right here. Next, I don't know, I noticed that most of this graph is negative, so let me try a negative value. If I do negative 1, let's see, 1 minus minus 1 is 1 plus 1, it's 2. And, ooh, that's going to be the square root of negative 1, which is bad because that's I. And that's an imaginary number. It's a complex number, but so is 0. Everything is a complex number, right? Almost everything. So let's make a note here that complex numbers are not allowed on, or I should say in AP Calculus. Cool, so we have that note here. So don't do that. I guess you could say if I'm limited to my real numbers, not imaginary numbers, then the answer here is not I, it's D and E. I'll put that in parentheses here. But okay, so how am I going to get negative numbers? Let's try, I guess I'm going to have to go positive 1. So 1 minus 1 is 0, and square root of 1 is 1. So 0 comma 1, let's graph u, 0 comma 1, all right. Wonder what's going on. Let's try 2. 2. 1 minus 2 is negative 1. Square root of 2 is, that's a bad number. And I don't have a calculator, so I know that this is about 1.3. But maybe what I should do is I should choose a perfect square for t. So if a t is 1, that's a perfect square. 2, 3, 4. Okay, so 4. And then 1 minus 4 is negative 3. And the square root of 4 is 2. So let's graph negative 3, 2. Negative 3, 2. Ooh, okay, this is looking familiar. And another perfect square, 9. 1 minus 9 is negative 8, and square root of 9 is 3, so negative 8, 3. Negative 8, 3, I guess that's the last thing I have room for in my graph. And I can't really choose any other values of t. And I'm asking myself, is it ever possible to have any of these negative values? Like, could it come back down this other way? Because so far all I have is this function. It should be a little bit more curvy than that. This function that comes down like this. That's what it's looked like since it's happening. And if you ever need to choose a value in between here and here, you could choose like 1/4 to see if that's what's really happening. Something that has a perfect square on the bottom. Can I ever have any negative y values? And the answer is, well, look at your y's. My y's are square roots, and the only way for this to be negative is if there was a negative out here. So no, I will never have anything down there, and there's my final answer. Again, I kind of want to check that. You can see that I've already kind of have it in. Oops. Let's get rid of that. That is not what oh, that is exactly what I wanted. Yeah, so from 1 minus t is my x, and the square root of t is my y. Yeah, it looks like a square root function. Like, let's look at a normal square root function. So if I do square root of x, it goes the other direction. So how do I flip it over the y-axis? Well, you make it negative on the inside. And then how do I shift it right? Well, if I ever need to shift right or left, it's always opposite. So if I do right 1, instead of doing +1, I'm going to do -1 on the inside. So -1. Sorry, I'm shifting it. I want to shift it right. So it's, oh, because I have to do parentheses. That's what's all messing me up. It's x minus 1. There it goes. If I had parentheses, then it is opposites. And yeah, it is a square root function. Nice. And let's move on to number 3. Okay, again, I need to set up my table. So values of t. My x values are going to be given by t squared minus 6t plus 8. And I should make my t slightly curlier so I can tell them apart from my pluses, plus 8. And my y values, which is just, again, t. I'm going to copy that down. All right, let's go ahead and make my columns. And then go ahead and make my top of the table look nice and formal. Again, I'm going to probably choose 0. So 0 minus 0 plus 8 is, I'm going to write it down, 0 minus 0 plus 8 is 8. And then I just copy down the t value again. So 8 comma 0. 8 comma 0 is right there. What's another good value to check? Check 1. That's going to be some, yeah, sure, why not? 1. So that's going to be 1 minus 6 plus 8. Negative 6 and 8 is 2, and then 2 plus this 1 is 3. And then I just copy that down as well. 3 comma 1. 3 comma 1. I'm noticing when I'm looking at this that this is a quadratic. I'm curious what happens if I factor this. And by all means, like, you can do whatever you want. You can keep going with the table. I'll probably be fine if I just continue the table. But I'm just curious, like, if I factor this, what happens? So I'm going to use my Ninja Star tool, and I ask myself, what adds to negative 6 and multiplies to 8? So first, what multiplies to 8? 1 and 8, it doesn't work. 2 and 4, oh yeah, 2 and 4 will somehow get 6. So I think I need both of them, yeah, both of them need to be negative, and then I factored it. So this is really, it's not x, but it's a t minus 2 and t minus 4. Which means if I choose my t value to be 2, or I choose my t value to be 4, I'll get 0. So let me skip, I would have done that next, right? That was my next step, 2. If I do 2, you can check it. 4 minus 6 times 2 is 12, plus 8, and yeah, that is indeed 0, and then I just copy down the t value. So 0 comma 2, 0, comma 2 is right there. And then the next value I want to check is that one to see if I'm really true. So 4, if I'm really correct. So 4 squared is 16 minus 6 times 4 is 24 plus 8. Yeah, again, that is equal to 0. And then I copy down the 4. So I'm going to come up here 0, 4. Can't quite tell what's happening. My prediction is I'm going to have some sort of parabola that goes like that. I'm not sure. How could I test that prediction? I guess I should have picked 3. Okay, so this is out of order. Just playing with my math here. This is going to be 9 minus 18 plus 8. Oh, this is going to be a negative number, which is what we wanted. Okay, so negative 18 and 8 is negative 10. Negative 10 and 9 is negative 1, 3. Okay, so negative 1, 3. Okay, so I was right. It is some sort of parabola thing. To verify that, let me plug in 5, and I should get this point out. That's my guess. I'm guessing I have like some sort of axis of symmetry here. I'm guessing I'm going to have 3, 5. So my prediction is that this is going to be 3, this is going to be 5, if I choose this to be 5. Well, 5 and 5 obviously match up. So 25 squared minus 6 times 5 is 30, plus 8. Why did I write squared? I don't know. 5 squared is 25. 25 minus 30 is a negative 5. Negative 5 plus 8 is indeed 3. Cool. So it is the parabola that I'm looking for. So I can use the axis of symmetry right here and say this point should also be up here at 8, 6. Whoa. I hit spacebar. Don't hit spacebar, kids. So right here. And let's go ahead and make our graph. So it comes out like that, and comes out like this. And I know this isn't supposed to be a sharp corner, it's supposed to be a gradual curve, but I'm not the best artist. I just need to work harder. The growth mindset. I will get good at art if I practice art. And then number 4. Let's try number 4. So again, values for t, and then x is just going to copy down t. Y is going to be t to the power of 3 plus t. I wonder what's going to happen here. So the x values are going to be kind of linear. This x is not going to be increasing very fast. The y value is going to be increasing really, really fast. Just like the y value already says is increasing fast. So if I change this to y equals x cubed plus x, I know that's some sort of cubic function. I'm wondering, is this just going to be a cubic? Guess we'll find out, won't we? You're hearing my inner thoughts when I would be doing your homework. So I always like 0 first. 0, that's going to be 0, and 0 plus 0 is 0. Okay, so 0, 0, the origin is going to be on there. Ooh, and this is scaled by the y, interestingly, so it's really compressed. That means it's going to scale really fast in the y-axis, like I was thinking. Let's try 1. When I choose 1, that's going to be 1 here. 1 cubed plus 1 is 2. 1 cubed plus 1 is 2, so 1, 2. 1, 2 is that point right there. Let's try 2. 2, that's going to be copied down. 2 cubed is 8. 8 plus 2 is 10. So 2, 10. 2, oh wow, it jumped up there quite a bit. So I'm seeing something that looks like that. What's happening with negative values? In order to get a negative x value, I just choose a negative t value, since x and t are the same thing. Let's choose negative 1. That means that's negative 1. That means negative 1 to the power of 3 is still negative 1, and then minus 1. So that's negative 2. And it's going to be symmetrical here, because these values are always going to match. So this next one, if I do negative 2, I'm just going to make these both negative. Negative 8 minus 2, and I'll get negative 10. These are all symmetric, like I say. Come down here, negative 1, 2, negative 2, 10. And yeah, this is just a positive cubic function. So let's sketch this with yellow. Sketch, 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 sketch. Oh, no, got off there a little bit. It comes up in that direction. And this really should, let me try to redo this bottom part. This really should flatten out a little bit more. So it comes down here and flattens off, and then comes back down. Again, need to practice this more. Comes down and then starts making your parabola shape back the other direction with the negative concavity and positive concavity up there. All right, cool. We're on to number 5. And I know I'm taking too long, but I'm kind of having fun doing this. Let's make a value or table for t values. X is equal to t squared and y is equal to t to the power of 4. All right. Making our columns. Oh, I want you to be slightly straighter. Thank you, sir. This one I can go a lot faster. So 0, it's going to be 0, 0. That means 0, 0 is on my graph. Let's choose 1. 1 squared is 1. 1 to the power of 4 is 1. 1, 1 is on my graph. Let's choose 2. 2 to the power of 2 is 4. 2 to the power of 4 is 16. Is that even available to us? No. Let's try... I'm going to get rid of that one then. Let's try negative 1. Negative 1 squared is 1. And 1 to the power of 4 is 1. So negative 1, 1. Sorry, negative 1. Or sorry, positive 1, positive 1. So it's the same coordinate. Darn it. What could I do here that would make it slightly different? 2 to the power of 4 is too big. So choose my t values to be slightly smaller. Let's try, yes. Cool, I'll get that later. Let's try something else. Let's try, wait, 2, why did 2 not work? 2 to the power of, I'm trying to think. 2, if I choose that, that's 4 and 16. That's 2. I'm trying to figure out, how do I get 2 there? Oh, I know how to get 2. So I could get 2 if I did the square root of 2, right? Let's try this. The square root of 2 would give me, and I squared that, and I get 2, and then I square that again, and I'd get 4. Hey, okay, that's the logic that I'm using here. So 2 comma 4. Oh, okay. Well, how do I get, can I ever get negative values? I'm trying to think here. Don't know if I can ever get negative values because I'm always going to be positive. I'm pretty sure it's just going to be this half of a quadratic. I think that's all we can do because we can never have negative values of x unless, no, yeah, I was thinking maybe we could do negative square root of 2. No, it's still a negative times a negative, which is a positive. I think that's our answer, just like that. Like that. Let's go ahead and check. Did I even check the last one? I didn't, but I'm really confident that I did that. Let's just double check that one really quick. So x is equal to t. We'll get rid of you. Do we need you? We can get this. So we'll say x is equal to t and y was equal to t to the power of 3 plus t. T to the power of 3 plus t. There we go. And what do you look like? Yep. So you are a, oh, wait, oh, can I go negative 2 pi? Ah, there we go. Okay. I was like, oh no, we messed up. There's no left-hand side. There's nothing that's a negative x value. Now we got that. So this graph matches up. Do we check this guy? I don't think we did. Let's go ahead and check him as well. T squared minus 6t, t to the power of 2, minus 6t plus 8. Ooh, weird things are happening, and this is all going to be just t. Yep, okay, we got him correct. And finally, down here, t squared and t to the power of 4, t squared and t to the power of 4. Yep, and notice that even though we have negative values of t, we can only stay on that right-hand side. So if you do put the rest of the parabola over here, the imaginary side, that doesn't exist. It's only over there. All right, so this is the part where we switch to the graphing calculator. For those of you that are still in pre-calculus, this means that you get to use just Desmos. Graph this on Desmos. And for those of you that are using the calculator, I will be doing that with you. So I'm going to just follow the instructions here. To graph, we are going to do the following. We're going to hit mode and go down to functions. So let me pull up my graphing calculator. Mode, and then I'm going to go down to functions, and we need to switch to parametric, P-A-R, so I hit right, enter. Okay, we're now in parametric mode, and our y equals, we're going to enter our two equations and then graph. So come over here to y equals, oh, we have an x and a y. So our x is 4 cosine of t. Oh, it actually does a t instead of an x now. And then this is going to be, oh, I still need to add, oh, come back here. This is going to be plus cosine of 12t. Cool. And then my y is going to be 4 sine of t plus sine of 12t. All right, and then we'll go ahead and, what should our window be? Our window, probably want to go from our t. Let's go from like negative 2 pi to 2 pi. Negative 2 pi to, oh, this is already 2 pi. 6.28 is 2 pi. And then I'm going to hit zoom 0 to zoom to scale and see what happens. And then I'm going to try to sketch him on here. Go. Whoa, whoa, crazy. Okay, so I'm just going to go around again because I'm going crazy here. So let me go ahead and take a screenshot of that and put it down. Oops, I put my stylus on the tablet and doesn't want to move my mouse. So take a screenshot of you. That's interesting. So that's what happens if I have the following conditions. If I did this, and I'll scroll down so I can take a picture of my window conditions. And so that's with that window. What happens if I change my conditions here a little bit? What if I instead do my x-min, x, do I have any, oh, the step. So this is how accurate it is. So I'm going to change my step to something small. It'll take my calculator longer to do, but it'll be cooler. So I probably just want to go from negative pi to pi. It'll be fine. I'm just going to change this to 0 actually. I think it should still be fine. And then this one is going to be my step. I'm going to do, instead of 0.13, I'm going to do 0.05, much, much smaller. And then I'm going to hit graph. Ooh, yeah, that's pretty. It's like you can compare the two graphs, right? One of them was very chunky because my step size was too big, and this one my step size is smaller, so I get to see a better graph. It does take a lot longer, but man, it was kind of worth it. And it's kind of pointless to wait this long for the calculator and see. Yeah, 0 to 2 pi was perfect. When I compared this to like Desmos would have done it in like instantly. So let's paste that on here. This is what happens if we have a slightly bigger step size. So I'll take a picture of this as well. Oh no, too far. All right, and we'll take a picture of our window as well. Boom, and paste that in here. And yeah, the main difference between these two, so if I have for the notes, is our step size. The step size is the thing that makes the difference, the more accurate. So then I have to do my best attempt to sketch this thing. Oh dear gosh, okay. And you can see it goes 1, 2, 3, 4, 5, and that's why it goes up to 5, and then 1, 2, 3, 4, 5, 5. So it's actually a perfect circle, and that's one of the reasons I don't like this calculator, because you can't tell that that was a, it's symmetric, it has radial symmetry. So how are we gonna do this thing? So I see a loop-de-loop that goes right there, right there, right there. Oh, it has to go right through the center, right there, right there. Oh man, I'm trying. Right there, and it goes through him, right there, and then back. Okay. Oh man, that was, maybe you'll do a better job, but there it is. What would it look like if we used Desmos? Let's get rid of you. So 4 cosine of t, so 4 cosine of t plus, and then what is it? Cosine of 12t plus cosine of 12t, and that's the x. Okay, the y is the same thing with just them swapped. So it's going to be 4 sine of t plus sine, they're both sine, right? Yeah, just make sure. Sine of 12t. And again, I'm going to go from 0 to 2 pi. And wow, yeah, so it did it instantly. It's kind of sad that we have to use this old calculator still, right? And that's much easier to draw. Well, sorry, but I have technology, so I'm going to just copy and paste this. It looks a lot better. I'm going to make it black, sure. And yeah, let's screenshot this bad boy. So come out to roughly -5, right about there. And pasty right on top of our graph. And yes, it doesn't look exactly right because it doesn't have the X and Y axis labeled, but man, yeah, that looks way better than Mr. Sandell's drawing. All right, let's do number 7. So again, on the calculator, how do we do this thing? I'm going to leave my step size nice and low at 0.05. And I think 0 to 2 pi is still going to be perfectly fine. So let's get rid of these. Clear. This is going to be 2 times 1 plus cosine of t, and the parentheses twice, times cosine of t. I don't have to hit the times button. I can just type in cosine of t. I'm confident knowing my orders of operations. Second one is going to be 2 times 1 plus cosine of t, and 2 parentheses, and then multiply by sine of t, and zoom 0. Let's go see what that looks like when we check it on Desmos. That looks nice. All right, so cool little heart-shaped cardioid here. Let's go ahead and paste that over here. Let's see what's going on here. There we go. And what does our graph show? It finished in time. Yeah, it's a squished cardioid because, yeah, the scaling for Desmos is nice because the X and Y are scaled with the same dimensions, and this one has to squish it because the screen is not a perfect square, so this doesn't really do it justice. But there it is. Might as well paste that in here as well. Cool. So there are the 2 different graphs. That is the answer for 7, and I'm done with worksheet 1-1. It's been a pleasure, guys. I'll see you later.